Many years ago, I bought this mobile, and the idea of this mobile is it's a sort of fluorescent green spring that rotates, and because the ball is just jammed into the middle of it, it gives this optical illusion that the ball is kind of staying put and the spring is running past it. It's quite a neat effect. But the reason I bought it was because it came with a rotator, a battery-operated rotator that came with this ridiculously huge battery life. And I was really intrigued as to how they did that. So initially I was thinking it was going to be, say for instance, that's the rotator up there, and it had this little loop underneath it and this sort of thread coming down onto the effect. And I thought initially it was just going to be a really low power geared motor, but it wasn't. It was an ordinary motor, and it wasn't geared. It was directly onto that. And inside were a couple of batteries and a little bit of circuitry. And it was all based around discrete circuitry at the time. And what it did was it would spin the motor really quickly for a very short period of time. Every so often you just see the engine sort of go brrr and then stop. And then after a sort of time delay, it would then spin in the opposite direction. It resulted in I'm pretty sure it spun in the opposite direction, but it resulted in continuous motion of the mobile with very low power consumption without any need for complex or noisy gearing. And I was thinking recently, what could you do that with? Because I found the mobile and I thought it'd be quite nice building my own rotator to do that using standard components. And the thing that came to mind was an air freshener, because it has the timer built in and it's got the motor, and more importantly in this case, I chose the one that only has a single direction, because with these things that push the plunger of the air freshener down, you get the two versions. You get the one that pushes it down and then relies on the spring pressure pushing it back up, or you get the version that winds it down and then winds it back up again. So the simplest one is the one that just winds it down, and that kind of suits this application as well. So what I did was I gutted that out and I put the circuitry into a little housing that could be screwed up to the ceiling or onto a frame. And the circuitry in this is very simple. It's using a little 8-pin chip, that classic 8-pin chip that's, just you find these in just about everything. It could be a range of different microcontrollers, but it is that classic form that, it's you find it in just everything. It's basically about, probably, it'll be a microcontroller, but it'll just be the smallest form that, they can conveniently get. And the motor, I took the motor of the air freshener out and I mounted it through this plastic box. And I originally used a pair of heavy-duty side cable cutters to actually cut round the plastic of the original air freshener to use the original mounting of this as a template, and just drilled straight through it and marked through it. And to attach the thread, the little pulley pulls off, so all I did was I tied the thread through it, knotted it a couple of times, and then just wedged it back on. So the thread is actually passing through the shaft, and it kind of grips onto that quite tightly. The circuitry in this is really simple. Hold on, where's my notepad? I've already doodled it out. I doodled it out last night. The chip is called an RB1401C, and the circuitry is, I'm just check this is in focus. Yes, it is in focus, because I usually have a separate, you know what, it's all going to be down here, so I might as well focus down there. Yeah, that's right. So it's got the two AA cells to create a 3-volt rail. It's got the little processor, which is marked RB1401C. That could be an actual chip, or it could be a proprietary marking. It's got a local decoupling capacitor across this. Now, see when you've got tracks on a printed circuit board where you've got a motor load or other high current load, you have to be careful not to have the microcontroller beyond those, so to speak, in the sense that when the motor runs, it can cause a sudden voltage fluctuation in that rail, and with some microcontrollers they're sensitive to that and can interpret it as, they can misinterpret zeros and ones, and it can cause them to crash. By starring the power from very close to the batteries, and also putting a little decoupling capacitor across, so even though you might get a sudden current flow along this line that causes a voltage gradient, by keeping it with its own little decoupling capacitor locally, that provides a little buffer local to the pins. That's why you often find these decoupling capacitors, because it just prevents those transients from having such a significant effect in the processor. But it's got the decoupling capacitor. It's got a transistor with a 180 ohm. It's just a standard transistor. I think it was marked Y1. Then it's got the motor with a diode, reverse polarity diode across that for the to protect the transistor, and it's got another little capacitor, presumably to protect against interference noise from the motor's brushes. The only other thing here is it had a 4-position switch: off, low, medium and high. And interestingly, the processor's powered all the time. I guess this is a cost-saving thing. And the switch is just it's an 8-pin switch, but they've just kind of used a standard switch, and they've bridged the tracks and pins in such a way that when it's off, it presents, well, in all positions, it presents a 2-bit binary number. 00 for off, 01 for low, 10 for medium, and 11 for high. So I found it's best to use the high setting for the most movement of the mobile. So that's effectively both those switches shut, so to speak, or the one switch in its fast position, its maximum aroma position, where it's going to be pumping that motor a lot. The chip itself, the pins, and maybe you can guess what it is from this pin out. The 2 inputs were at this end. This pin wasn't connected. This one was marked a test point. It was out to a wee pad locally. It's got the output through the resistor to the transistor. And then it's those 2 pins. I'm not sure if there's any reason, but they were both connected to the negative. And then this pin was the positive, which is quite an odd pin out. Certainly not in the usual sort of PIC microcontroller range of things. So this works. It works quite well. What actually happens here is that when it spins, it winds up the thread. And if this was connected rigidly to the mobile, you'd get a burst of movement and it would stop. But what actually happens is, because it just spins every so often, I measured about 50 revolutions, it winds this thread up, and the inertia is such that the mobile in the end couldn't just instantly launch into action. So it uses the thread to store that rotational movement. And then, because the thread's wanting to straighten out again under gravity, the mobile then just keeps rotating continually until it's used that twist it up, and then usually by that time it'll have put another twist in that's kind of self-regulating, because the more it twists it, if it kept running, well, if you ran it all the time, it would probably wind this thread up into little knots, but it would be trying to rotate the mobile as fast as possible. But because as it untwists, the mobile gradually gets slower, it just self-regulates. I mean, the speed will vary up and down, but it has a sort of self-regulating effect depending on how much twist is in the thread. It's very clever. It's very simple. I wonder who came up with the original idea. So you can turn an ordinary air freshener, like this, into a mobile rotator with little more than a battery pack and a new case for the motor. Very, very simple. So there's the unit attached to a door frame and a bit of thread, and there's the mobile hanging on the end, just spinning away merrily. It's working quite well. Yeah, that's quite a good result. It's whenever you walk past it, there's always some level of movement at a random speed. It looks okay.